Alright, welcome to video part 1 of topics 3.2, interactions between molecules. In this video, we'll be looking at first few boxes there. Firstly, the physical properties of molecular substances can be explained by considering the nature and strength of the forces of attraction between the molecules. Secondly, secondary interactions between molecules are much weaker than primary metallic, ionic, and covalent bonds. And also, the third one there, the shape, polarity, and size of molecules can be used to explain and predict the nature and strength of secondary interactions. So let's look into that. So, primary bonds, just to recap, it's intramolecular bonds. So those three primary bonds are metallic, covalent, and ionic. They operate within molecules. On the other hand, secondary interactions happen, which are intermolecular forces, like international or interstellar, happens between things, operates between molecules instead of within molecules. It's between. So there are three different types of intermolecular forces, and you will be familiar with all these three. First one is dispersion forces. Secondly, dipole forces, and finally, hydrogen bonding. So they are the secondary interactions, and they are much weaker than intramolecular bonds. Intramolecular bonds are bonds. Electrons are fixed and they don't move, whereas interactions are just interaction between molecules, like this one here. So it's showing a diagram of how you should draw hydrogen bonding that's happening between water molecules. Again, it's water molecules, and intermolecular bonds are something that happens between molecules. Covalent bond is also pointed out. That's happening between oxygen and hydrogen atom, that is within a molecule. Hope you see the difference there. All right, moving on to the first one. Say that this oval that I'm showing there, I'll zoom in a bit, is the a molecule, any molecule. It's got certain number of electrons, so those purple dots are electrons. Now, those electrons are moving around, and at some stage, there's a chance of those electrons being collected on one side. Now, when that happens, when electrons are located or just crammed together in one area, you can have a more negatively charged area and more positively charged area. We call that as temporary dipoles. So draw that. Temporary dipoles. Now, when many molecules were present, which should be in any, say, beaker or whatever, those temporary dipole happens to, many molecules like so. So there are 4 of the same, and they all have got temporary dipoles, delta negative and delta positive ends. What they can do is to start interacting. So negatively charged part are going to be attracted to positively charged, so I should say partially positively charged part of another molecule, and that could be attracting a negative part of partially negative part of another molecule, and so on. Opposite charges of the temporary dipoles create an electrostatic force of attraction between molecules. Now, something that you have to understand is that this happens temporary. They're not fixed. Electrons will start moving again. So there may be some interaction happening between molecules, but they can fly apart fairly easily as well. Now, all substances have this dispersion force. All substances. Okay? Non-polar substances, they only have this interaction. If you have got polar covalent bond, HCl in that example there, in this way, on the left hand side for you, the HCl have got a very polar bond there, and that shows that there will always going to be positive and negative end. So you will have interaction between HCl molecules all the time. On the other hand, if you have hydrogen gas, which is just above here, hydrogen gas, hydrogen to hydrogen share electrons, and that bond is non-polar. And also that makes the whole molecule of hydrogen as non-polar. What interactions are available between H2 and another H2? Only the dispersion force, because that's what non-polar covalent bond can do. Now, speaking of polarity, let's look at the polar and non-polar argument again. So it says, when electrons are shared unequally, this creates what is called to be a partial charge around the atoms in the bond. And when I say partial, you would use delta plus and delta minus symbols. Okay, they are the convention that you have to be able to use or draw, right? How are electrons shared in the following compound? So have a look at that. So CO2 and also HCl, very similar as what we did before. So in Cl2, you can see the cloud is equally sharing, and in HCl, you've got the cloud on chlorine side being bigger than H. You can say that CO2 is non-polar, whereas HCl has got delta negative and positive. Therefore, there's a polar bond. Sorry about the font color. I don't know why it appeared in black, but yeah, it's a polar molecule. Now, this also allows you to see what happens if you put polar and polar stuff together or polar and non-polar stuff together. Now, there's what's known as like dissolves like rule. So this rule says that if you have polar substance, that would dissolve in polar thing. And if you have non-polar substance, that would dissolve into non-polar substance. Think of paint. Oil paint and water-based paint, they don't mix well. Oil paint can be only thin with paraffin oil. If you want to use water-based paint, you would dissolve that into water and thin it. Same deal. Polar molecules contain partial charges, therefore they are attracted to other charged particles, including other polar molecules. Think of polar substance like HCl into water. They're polar and polar. When polar and non-polar substances are mixed, think of oil and water, the polar molecules attract each other, but not the non-polar molecules. If you watch the video clip that's linked in that, why don't oil and water mix, it explains it quite well. We'll watch that in class too. And thus, the two substances would separate into layers. Think of oil just floating above water. This is what happens to oil, non-polar substances, and water. There you go. They don't mix. We'll probably do demo of having chewing gum, which doesn't dissolve in your mouth. But if you put something oily, like chocolate, it melts, or dissolves, shouldn't say melt, it dissolves away. We'll do that as practical demo. Another thing about polar and non-polar, polar substances can only dissolve into other polar substances, like polar bear dissolving, no, just kidding. Non-polar substances can only dissolve in other non-polar substances. Chemists call this as like dissolves like. That's what we've been talking about. What is used to protect things from rain? Think of something that doesn't dissolve into water. What other containers used to store acids? Acids always have positively charged ion that can they can come off from the compound if it's in water. So what would you use to keep that, store that? This is a slide for next video, so I'll cut this off. All right, I'll see you in the second video.